There is a moment, just before dawn, when the world holds its breath. The darkness has not yet lifted, but somehow you sense that light is coming. Perhaps it's the way the air feels different, or how the silence seems to deepen just before the first birds begin to stir. In October of 2017, on the slopes of Haleakala volcano in Hawaii, something like this moment was unfolding in the realm of distant starlight. The Pan-STARRS telescope, its name a gentle acronym that rolls off the tongue like a whispered prayer, had been sweeping the sky as it did every clear night, patient and methodical. Its electronic eye gathered photons that had traveled unimaginable distances, each point of light a story written in the language of physics and time. But on this particular night, October 19th, something appeared in the data that shouldn't have been there. Robert Warwick, the astronomer who first spotted it, might have felt that same pre-dawn sensation, and knowing that something had shifted in the familiar patterns he studied. Among the countless dots of light that painted his computer screen, one small point was moved, not in the predictable way that asteroids move, bound by our sun's gravity in their endless loops around the inner solar system. This visitor was different. It was moving too fast, and worse yet, it was moving wrong. The object, still nameless then, just a string of numbers and coordinates, was traveling at more than 26 kilometers per second relative to our sun. To put that in perspective, imagine driving from New York to Los Angeles in about 6 minutes. But even that comparison feels inadequate when we consider that this traveler had been moving through the darkness between stars for perhaps millions of years before our sun's light first touched it. What makes a visitor from interstellar space so fundamentally different from anything we'd seen before? In the days that followed its discovery, telescopes around the world turned their attention to this small, fast-moving speck. The European Southern Observatory in Chile, the Gemini Observatory, the Hubble Space Telescope, all began to track its path and measure its light. What they found painted a picture of something that had traveled here from somewhere else entirely, somewhere beyond the reach of our sun's influence, beyond the comfortable boundaries of what we call home. The object was given a name that honored both its discovery and its nature: ʻOumuamua, a Hawaiian word that means scout or messenger. The okina, that small mark before the O, represents a glottal stop in Hawaiian, a brief pause in speech, like the moment between breaths. Perhaps that pause is fitting for something that represents a pause in our understanding of what moves through the cosmos. Picture a single leaf detached from its tree, drifting on an autumn wind. But imagine that wind is the space between star systems, and the journey lasts not minutes but eons. As October gave way to November, Oumuamua continued its swift passage through our solar system. It had already made its closest approach to the sun by the time we discovered it, swinging around our star like a stone cast across a vast pond, using our sun's gravity to slightly bend its trajectory before continuing on its way toward the constellation Pegasus. By the time astronomers began to understand what they were looking at, their visitor was already saying goodbye. The realization settled over the astronomical community like morning mist. This was the first confirmed object from interstellar space ever observed passing through our solar system. For generations, scientists had theorized that such objects must exist debris from other star systems, cast out by gravitational interactions and sent wandering through the galaxy. But theory and observation are different creatures entirely. One lives in the realm of mathematics and possibility. The other requires light, time, and the patient act of seeing. Of course, we should remember that our observations were limited by the brief time we had to study this visitor, and much about ʻOumuamua remains wrapped in gentle mystery. What struck researchers most profoundly was not just that they had found an interstellar object, but how ordinary the finding had been. There was no dramatic announcement, no sudden revelation, just a routine observation on a routine night, the kind of patient sky-watching that astronomers perform every clear evening around the world. In this ordinariness perhaps lies something beautiful. The universe occasionally offers its gifts, not through cosmic drama, but through the quiet persistence of human curiosity. But what was this object, really? What shape did it take as it tumbled through space, and what could its strange behavior tell us about its long journey? The light reflected from ʻOumuamua told a story that grew more intriguing with each observation. As it rotated, tumbling end over end in the way that objects do when they're not bound by gravitational forces that might stabilize them, its brightness changed dramatically. The variations suggested something highly elongated, perhaps 10 times longer than it was wide. Imagine a cosmic cigar, or maybe a needle spinning slowly as it sailed through the darkness. But even this picture, dramatic as it was, couldn't fully explain what telescopes were seeing. Some observations suggested the object might be even more unusual, perhaps not a cigar-shaped rock at all, but something flat and broad, like a cosmic pancake tumbling through space. The uncertainty wasn't frustrating so much as mysterious, in the way that all the best cosmic discoveries maintain an element of gentle enigma. As November deepened and Oumuamua grew fainter and more distant, another puzzle emerged. The object wasn't following quite the trajectory that pure gravitational forces would predict. Something was giving it a tiny additional push away from the sun. Not much, just a few centimeters per second squared of acceleration, but enough to be measurable. It was as if the visitor had its own faint means of propulsion. What invisible forces might act on a traveler that has journeyed so far from home? The most likely explanation was something beautifully simple: sunlight itself. When photons from our sun struck the surface of Oumuamua and bounced away, they would impart a tiny amount of momentum, like throwing ping-pong balls at a balloon. This radiation pressure, barely noticeable for most objects, might be significant for something with just the right shape and composition. Perhaps something light and broad, like a thin pancake spinning through space. Though we should note that this explanation, elegant as it seems, is based on our best understanding with limited data, and Oumuamua may yet hold surprises. By December, our visitor had become too faint to observe, even with our most powerful telescopes. It passed beyond the orbit of Mars and continued outward, carrying its secrets with it toward interstellar space. In a few thousand years, it will be farther from our sun than the nearest star. In a few million years, it will be crossing the space between star systems once again, perhaps eventually encountering another planetary system, maybe one with astronomers of their own to puzzle over its passage. We can rest here for a moment, in the quiet satisfaction of having witnessed something unprecedented, humanity's first glimpse of a confirmed messenger from beyond our solar system, a traveler that had seen other suns, crossed distances that challenge our imagination, and briefly shared our small corner of the galaxy before continuing its ancient journey. The final image is this: a point of light growing dimmer among the stars, carrying its mysteries back into the vast darkness from which it came. There are numbers that live quietly in the background of our daily lives. The distance to the grocery store, the time it takes to brew coffee, the age of the oak tree in your yard. These are comfortable numbers, numbers that fit within the boundaries of human experience. But there are other numbers, cosmic numbers, that exist in a realm so vast that our minds can only approach them through metaphor and gentle approximation. Consider the space between stars. Even our nearest stellar neighbor, Proxima Centauri, lies more than 4 light-years away. That distance, about 25 trillion miles, is so immense that if you could drive there at highway speeds, without stopping, the journey would take nearly 30 million years, long enough for entire species to evolve and disappear while you traveled. This is the ocean that Oumuamua had been crossing before it arrived in our solar system. Not the empty vacuum that we sometimes imagine space to be, but a realm filled with invisible currents, magnetic fields that stretch between stars, thin wisps of gas and dust, and the gentle pressure of starlight itself. A place where objects can wander for millions or billions of years, following trajectories written by the gravitational signatures of distant suns. Feel the softness of whatever surface supports you now, the immediate comfort of gravity holding you in place. Oumuamua had known no such anchor for eons beyond counting. What makes an object truly interstellar is not just distance, but velocity. Everything in our solar system, every asteroid, comet, and grain of cosmic dust, moves in patterns orchestrated by our sun's gravity. Like dancers in a vast, slow waltz, they follow elliptical paths that bring them close to our star and then carry them away again, only to return in their appointed time. That an interstellar object moves to a different rhythm entirely. When astronomers first calculated Oumuamua's trajectory, they found something that had never been seen before: a hyperbolic orbit, where the familiar objects of our solar system trace ellipses, closed loops that repeat endlessly. Oumuamua followed an open curve. It approached our sun from the direction of the bright star Vega, swept through the inner solar system in a graceful arc, and continued outward toward the constellation Pegasus. A visitor, not a resident. Picture a leaf falling from a tree on a windless day, following a predictable path toward the ground. Now imagine that same leaf caught by a sudden gust that carries it up and away, over rooftops and beyond the horizon. Oumuamua was that leaf, and interstellar space was the wind. The mathematics that describe such journeys are surprisingly elegant, where bound objects follow Kepler's laws, those precise equations that Johannes Kepler derived 4 centuries ago by studying the motion of Mars. Interstellar visitors obey the same fundamental physics, but with one crucial difference: they carry enough energy to escape. Their motion speaks not of eternal return, but of permanent departure. To understand how rare such visitors might be, astronomers have spent decades modeling the space between stars. Their calculations suggest that interstellar objects should be drifting through our solar system all the time, perhaps 1 or 2 crossing Earth's orbital distance from the Sun every year. But until Oumuamua, we had never definitively seen one. This absence wasn't because they weren't there, but because they're almost impossible to detect. Most interstellar objects would be small, dark, and moving quickly through our cosmic neighborhood, like trying to spot a single raindrop in a storm by flashlight. Finding them requires both extraordinary patience and a measure of luck. Listen to the rhythm of your own breathing, steady and unhurried. Astronomers have learned to breathe with similar patience, knowing that the universe reveals its secrets not to those who demand immediate answers, but to those who wait and watch with quiet attention. The telescopes that hunt for such objects, Pan-STARRS in Hawaii, the Catalina Sky Survey in Arizona, Linear in New Mexico, scan the same patches of sky repeatedly, night after night, looking for anything that moves against the background of distant stars. Their work requires a particular kind of devotion, the willingness to sift through thousands of ordinary observations for the possibility of encountering something extraordinary. Most of what they find follows expected patterns: near-Earth asteroids that might someday pose a threat to our planet, comets returning from the distant Kuiper Belt, trailing their characteristic tails of sublimated ice, the occasional piece of space debris, humanity's own contribution to the cosmic environment. But once, on that October night in 2017, the patient mathematics of sky surveys yielded something unprecedented. The discovery process itself is poetry written in data. First comes the automated detection, computer algorithms trained to recognize motion against stillness. Then human eyes must verify what the machines have found. Astronomers like Robert Werrick studying dot patterns on screens, looking for the subtle signatures that distinguish the significant from the routine. In Oumuamua's case, that signature was velocity. Not just speed, but direction. The telltale angle that marked this object as coming from interstellar space. The computers flagged it immediately as unusual, but it took human intuition to understand the magnitude of what had been found. How do we measure the distance to something so far away and moving so quickly? The process requires a kind of cosmic triangulation, using observations from multiple locations and times to construct a 3-dimensional picture of the object's motion through space, like determining the speed of a distant airplane by watching how its position changes against the landscape, but extended into the realm of astronomical precision. The measurements revealed not just where Oumuamua was going, but where it had come from, tracing its trajectory backward through time. Astronomers could see that roughly 300,000 years ago, this object had passed within about 1.5 light-years of a red dwarf star, in the constellation Lyra, not close enough to suggest that star is Oumuamua's origin, but perhaps close enough to have influenced its journey in subtle ways. Before that encounter, the trail grows fainter, dissolving into the statistical uncertainty that surrounds all ancient journeys. Oumuamua might have wandered the galaxy for millions of years, its path influenced by the gravitational fields of countless stars, slowly spiraling through the Milky Way's vast disk like a leaf carried by invisible currents. Feel the weight of deep time settling around you like a comfortable blanket. These are journeys that span geological ages, movements so slow and vast that they exist in a different realm of experience than anything we know directly. The space through which Oumuamua traveled is not empty, though it might seem so to our limited senses. Interstellar space contains roughly 1 hydrogen atom per cubic centimeter, a density so low that it approaches perfect vacuum by terrestrial standards. Yet across the vast distances involved, this thin medium can exert measurable effects on objects passing through it. There are magnetic fields too, stretched between stars like invisible webs, carrying energy and organizing the thin gases of the galactic disk. Cosmic rays, high-energy particles accelerated by exploding stars and other violent events, streak through this medium at nearly the speed of light. And everywhere there is the subtle pressure of starlight itself, photons carrying momentum as they travel outward from billions of distant suns. For most of its journey, Oumuamua would have experienced these influences as whispers, forces so gentle that they would require millions of years to produce noticeable changes in trajectory. But as it approached our solar system, entering the realm where our sun's influence begins to dominate, more dramatic effects would have begun to manifest. The sun's gravity reached out to embrace our visitor long before it became visible to our telescopes. At distances measured in thousands of astronomical units, where 1 astronomical unit is the distance from Earth to the Sun, Oumuamua would have begun to feel our star's pull, its straight-line motion through interstellar space gradually bending into the hyperbolic curve that would carry it through our cosmic neighborhood. This is the mathematics of wandering, precise equations that describe trajectories spanning millions of years, velocities that carry objects across distances we can barely comprehend, and the patient work of observers who learn to see patterns in the apparent chaos of cosmic motion. Through such mathematics, we begin to glimpse the larger choreography of our galaxy, the slow dance of matter and energy that connects star to star across the vastness of space. Rest here in the wonder of it. Numbers so large they become poetry, distances so vast they approach the mystical, and yet all of it governed by the same fundamental laws that govern the fall of raindrops and the orbit of our moon. In the old stories, travelers from distant lands could be recognized by their unusual dress, their unfamiliar accents, the strange tools they carried. Oumuamua came to us wearing light, the faint sunlight it reflected as it tumbled through space, and in that light astronomers could read the story of its shape like fortune-tellers reading tea leaves. But cosmic visitors do not reveal their secrets easily. They speak in whispers of reflected photons, in the subtle variations of brightness that change as they rotate, in the spectra that reveal which elements absorb and scatter light at different wavelengths. To understand Oumuamua's true form required patience, careful observation, and the willingness to embrace uncertainty. The first clue came from the way its brightness changed over time. As telescopes around the world tracked our visitor through October and November of 2017, they noticed something remarkable. Every 7.3 hours, Oumuamua would grow bright, then dim, then bright again. This regular pulsing suggested an object that was tumbling end over end, presenting different cross-sections to our view as it rotated. Imagine standing beside a country road at dusk, watching the headlights of distant cars. When a car travels directly toward or away from you, its lights appear steady. But if that same car were tumbling, rolling over and over as it moved, the lights would appear to flash on and off as they alternately faced you and pointed away. Oumuamua's light variations followed a similar pattern, but the story they told was more complex than simple tumbling. The magnitude of the brightness changes was extraordinary. At its brightest, Oumuamua reflected nearly 10 times more light than at its dimmest. For a roughly spherical object like most asteroids, such dramatic variations would be impossible. The observations painted a picture of something highly elongated, a cosmic needle or cigar perhaps 10 times longer than it was wide. Close your eyes and picture this strange visitor, a dark, reddish object, tumbling slowly through the emptiness between planets. Its surface, aged by millions of years of exposure to cosmic radiation, would have the deep, weathered color of rust or dried blood. No atmosphere protects it. No magnetic field shields it from the harsh environment of space. It moves in silence, carrying its secrets across the vast distances between stars. But even this dramatic picture, a needle-shaped asteroid unlike anything in our solar system, could not fully explain what telescopes were seeing. As observations continued, and more data accumulated, some researchers began to suspect that Oumuamua might be even stranger than first imagined. What if, instead of a long, thin cigar, our visitor was actually flat and broad, a cosmic pancake tumbling through space? Such a shape could also produce dramatic brightness variations if it were thin enough, presenting its broad face at maximum brightness and its narrow edge when dimmest. The mathematics of reflected light supported both interpretations, a very long needle or a very flat disk, both equally alien to our experience of solar system objects. The uncertainty was not a failure of observation, but rather a reminder of how little light Oumuamua had to offer. Even at its closest approach to Earth, our visitor remained incredibly faint, roughly 4 billion times dimmer than the faintest star visible to the naked eye. Detecting it at all required telescopes among the most sensitive on Earth, and even then, Astronomers were working at the very edge of what current technology could accomplish. Feel the darkness gathering around you now. The way shadows deepen as evening settles. Oumuamua spent most of its time in similar darkness, illuminated only by the faint light of distant stars. Only during its brief passage through our solar system did it experience the full brightness of a nearby sun, and even then, that illumination lasted mere months before fading back into cosmic twilight. As December approached and Oumuamua grew more distant, telescopes strained to gather every available photon. The Spitzer Space Telescope, designed to observe in infrared light, turned its attention to our departing visitor, but could detect no thermal emission, the faint heat signature that most objects radiate into space. This non-detection provided another clue about Oumuamua's nature. It was either very small, very reflective, or both. The colors of reflected light told their own story. Oumuamua appeared distinctly reddish, similar to many objects in the outer regions of our solar system that have been darkened and reddened by eons of radiation exposure. This coloration suggested a surface rich in organic compounds, complex carbon-based molecules that form naturally in the cold, radiation-rich environment of space. Such organic compounds are common throughout the galaxy. They form in the atmospheres of aging stars, in the dense clouds where new stars are born, and on the surfaces of small bodies exposed to cosmic radiation over geological time. Finding them on an interstellar object was not surprising, but it did provide reassurance that Oumuamua was likely a natural object, a piece of rocky or icy debris from some distant star system, rather than anything more exotic. But it was the motion of Oumuamua, more than its color or shape, that proved most puzzling. As astronomers refined their calculations of its trajectory, they discovered something unexpected. The object was not following quite the path that gravity alone would predict. Something was giving it a tiny additional push away from the sun. The acceleration was minute, just a few centimeters per second squared, barely measurable even with our most precise instruments. But it was real, and it was consistent, acting like a very gentle rocket engine that operated continuously as Oumuamua moved through the inner solar system, in the quiet of your resting place. Consider forces so subtle they can barely be measured, yet persistent enough to alter the course of a journey spanning light years. This is the realm of radiation pressure, where light itself carries momentum and can nudge objects through space. When sunlight strikes any object, it imparts a tiny amount of momentum, the same principle that allows solar sails to propel spacecraft through the solar system. For most asteroids and comets, this radiation pressure is negligible compared to gravitational forces, but for an object with just the right combination of size, shape, and reflectivity, the push of sunlight can become measurable. The most likely explanation for Oumuamua's anomalous acceleration was that it had exactly such properties. Perhaps it was indeed pancake-shaped, thin, and broad enough that sunlight could provide significant thrust, or perhaps its surface had unusual reflective properties that enhanced the radiation pressure effect. The uncertainty in shape that had puzzled astronomers suddenly became a potential solution to the mystery of motion. This explanation, elegant in its simplicity, suggested that Oumuamua might represent an entirely new class of object, natural light sails created by processes we don't yet understand. Perhaps they form when larger bodies are disrupted by tidal forces near stars. Perhaps they're the result of collisions in distant asteroid belts. Or perhaps they represent some other phenomenon entirely, something we haven't yet imagined because we've never had reason to consider it. The beauty of this mystery lies not in having definitive answers, but in the questions it opens. How many such objects might be drifting through interstellar space? What processes create them? Are they common throughout the galaxy, or was Oumuamua's visit a once-in-a-lifetime event? As winter deepened and Oumuamua faded beyond the reach of even our most powerful telescopes, these questions remained suspended in the darkness like stars waiting to be discovered. Our visitor had shared its light with us for barely 2 months, but in that brief time it had expanded our understanding of what might exist in the vast spaces between suns. The last observations came in early January 2018, when Oumuamua had already passed beyond the orbit of Mars. By then, it was little more than a faint point of light, indistinguishable from the background stars, except for its motion. Soon even that motion would become too subtle to detect, and our cosmic visitor would disappear back into the anonymity of deep space. But the questions it raised would persist, driving new research and inspiring new observations, somewhere out there perhaps, Other needle-shaped or pancake-thin objects are following their own lonely trajectories between the stars, carrying their own mysteries through the cosmic dark. And perhaps, if we watch with sufficient patience and care, we will be fortunate enough to glimpse another such visitor, another messenger from the spaces beyond our solar system's embrace. Rest in the wonder of this uncertainty, this gentle mystery that reminds us how much we still have to learn about the universe we inhabit. Sometimes the most beautiful discoveries are not answers, but better questions. Questions that invite us to look more carefully, think more deeply, and remain open to possibilities we haven't yet imagined. There is a particular quality to the silence that surrounds astronomical observatories. It's different from the quiet of a forest or the hush of a library. It's a silence that seems to reach upward, extending beyond the atmosphere, into the vast emptiness where stars burn in solitude. Standing beneath the dome of a great telescope on a clear night, you can almost feel the universe listening back. The art of detecting objects like Oumuamua is fundamentally an art of patience. It requires the kind of deep, sustained attention that our modern world rarely demands. While most of us live our lives measured in minutes and hours, astronomers work on timescales that stretch across seasons and years, watching for changes so subtle they might escape notice if observed for mere moments. Consider the challenge. Somewhere in the darkness above us, a small object no larger than a city block is moving at tremendous speed through space. It reflects no light of its own, appearing only as a faint point in the reflected glow of our sun, against the backdrop of millions of stars, each casting their own ancient light across impossible distances. How do we learn to see such a visitor? The answer lies in motion. While stars appear fixed in their positions from night to night, their movements detectable only across centuries or millennia, objects within our solar system shift their positions in patterns we can observe and measure. Asteroids trace slow paths across the starfields. Comets sweep in from the outer darkness, growing bright as they approach the sun, and very rarely, something moves in a way that suggests it has come from somewhere else entirely. Let your breathing slow and deepen as we explore this patient art of cosmic observation. Feel the rhythm of your breath matching the rhythm of discovery. Long periods of quiet, watching punctuated by moments of recognition. The telescopes that hunt for these cosmic visitors are marvels of precision engineering. Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, sweeps across vast sections of sky each night, photographing the same regions repeatedly and comparing the images for any signs of change. Its electronic eye is sensitive enough to detect objects millions of times fainter than anything visible to the naked eye, yet precise enough to measure positions to within fractions of an arc-second. An arc-second is a unit of angular measurement, so small it defies intuitive understanding. It's roughly the apparent size of a dime viewed from 4 miles away. When astronomers speak of measuring positions to such precision, they're describing a level of accuracy that allows them to detect the motion of distant objects across the span of a single night's observations. The process begins in darkness, as telescopes across the world begin their nightly ritual of sky surveying. In Hawaii, Pan-STARRS starts its systematic sweep across the celestial sphere. In Arizona, the Catalina Sky Survey begins its own patient hunt. In New Mexico, the Lincoln Near-Earth Asteroid Research Program continues its vigilant watch. Each facility operates independently, yet all are connected by the shared purpose of mapping the moving objects in our cosmic neighborhood. The raw material of discovery consists of digital images, millions of them, captured night after night, season after season. Each image contains hundreds of thousands of points of light, most of them stars whose positions have been mapped with extraordinary precision. The challenge lies in recognizing when something new appears among this familiar stellar landscape, or when a known object begins to behave in unexpected ways. Modern astronomy has become, in many ways, a collaboration between human intuition and artificial intelligence. Computer algorithms process the nightly harvest of images, comparing new observations with vast databases of known objects, flagging anything that moves in an unusual pattern or appears where nothing was seen before. But the final recognition of significance, the moment when data becomes discovery, still requires human insight. Picture the moment when Robert Warwick first examined the data that would reveal Oumuamua on his computer screen. A simple visualization, points of light against darkness, with vectors showing the direction and speed of motion for objects that had moved between observations. Most of these vectors would point in predictable directions, following the orbital mechanics of asteroids and comets bound to our solar system, but one vector pointed elsewhere, suggesting motion that didn't fit the familiar patterns. The recognition might have come as a subtle shift in attention, the way your eye is drawn to movement at the edge of your vision, or perhaps it manifested as a feeling of wrongness, the sense that something didn't belong in the orderly mathematics of celestial mechanics. Whatever the initial trigger, it led to a closer examination, then to calculations that revealed the true nature of what had been found. This is how the universe speaks to us, not in dramatic pronouncements, but in the quiet language of precise measurement and patient observation. The cosmic background radiation that tells us about the early universe whispers to us through radio telescopes. Gravitational waves from colliding black holes reveal themselves as distortions, so minute they change the length of 4-kilometer laser interferometers by less than the width of a proton, and interstellar visitors announce their presence through subtle deviations in datasets that must be analyzed by the most sophisticated computers on Earth. Feel the profound silence that surrounds this kind of listening. In observatories around the world, astronomers work through the night in hushed concentration, their eyes adapted to red light that won't interfere with sensitive cameras, their movements deliberate and careful to avoid vibrations that might blur crucial observations. The instruments they use represent the culmination of centuries of optical innovation. The mirrors that gather starlight are polished to perfection, their surfaces accurate to within a few billionths of an inch. The cameras that record these images employ sensors cooled to temperatures hundreds of degrees below freezing, reducing thermal noise to levels that allow them to detect individual photons arriving from across the galaxy. Yet for all their technological sophistication, these instruments are simply extensions of human senses, electronic eyes that can see farther and more clearly than our biological ones, but still dependent on human minds to interpret what they reveal. The process of discovery remains fundamentally human. The application of curiosity, pattern recognition, and intuition to the vast datasets that modern astronomy generates. When Oumuamua first appeared in Pan-STARRS data, it looked unremarkable, just another faint point of light among millions. The computer algorithms that process such data are programmed to flag unusual motion, but they can't evaluate context or recognize unprecedented phenomena. That recognition required human expertise, the accumulated wisdom of astronomers who understood what normal motion looks like and could recognize when something departed from those expectations. The follow-up observations that confirmed Oumuamua's interstellar nature involved a worldwide network of telescopes, each contributing pieces to a puzzle that could only be solved through international collaboration. The European Southern Observatory in Chile provided crucial spectroscopic data. The Gemini Observatory tracked the object's changing position. The Hubble Space Telescope measured its rotation rate and refined estimates of its size and shape. This collaborative process reflects something beautiful about modern astronomy, the way individual discoveries emerge from collective effort, built on decades of patient work by observers whose names may never be widely known, but whose contributions make breakthrough moments possible. Every image archived, every measurement recorded, every algorithm refined, contributes to our expanding ability to see and understand the cosmos around us. Consider the infrastructure that makes such discoveries possible. Somewhere, power plants generate electricity that flows through cables to mountaintop observatories. Technicians maintain sensitive equipment in environments where temperature and humidity must be controlled to precise tolerances. Computer scientists develop software that can process terabytes of data in real time. All of this effort serves the simple goal of gathering light-ancient photons that have traveled across space to tell us stories about worlds we will never visit directly. The light that revealed Oumuamua to our instruments began its journey from the Sun roughly 8 minutes before reaching our visitor's surface. There it reflected into space, carrying with it information encoded in subtle changes of intensity and wavelength. Some small fraction of that reflected light continued across the 33 million kilometers that separated Oumuamua from Earth in October 2017, arriving at our telescopes as a whisper of electromagnetic radiation barely distinguishable from the cosmic background. That whisper contained everything we could learn about our visitor, its approximate size, inferred from the total amount of light reflected, its rotation period, encoded in the regular variations of brightness, its color, revealed through observations at different wavelengths, and its composition, suggested by the spectroscopic fingerprints of materials on its surface. Rest in the wonder of this cosmic telecommunications system. light carrying messages across distances that challenge imagination, decoded by instruments that represent the finest achievements of human technology and ingenuity. Through such methods, we extend our senses into realms we can never visit directly, learning to read the universe's stories written in the language of electromagnetic radiation. The art of cosmic listening requires more than sensitive instruments and sophisticated computers. It demands a particular kind of mental discipline, the ability to remain alert for the unexpected while processing vast amounts of routine data. Most observations reveal exactly what astronomers expect to find. Most objects move in predictable ways. Most data fits comfortably within existing models of how the universe works. But occasionally something appears that doesn't fit. A star that varies in brightness in ways that suggest the presence of unknown objects in orbit around it. A gravitational wave signal that implies black holes more massive than theory suggests should exist. Or a small object moving through our solar system in a way that suggests it has come from interstellar space. Recognizing such anomalies requires both deep expertise and intellectual humility. The knowledge to understand what constitutes normal behavior, combined with the wisdom to remain open to phenomena that transcend our current understanding. It's a delicate balance between skepticism and wonder, between the demand for rigorous proof and the recognition that the universe frequently surprises us with realities stranger than our theories predict. The detection of Oumuamua represents a triumph of this balanced approach. The observations were carefully verified through multiple, independent measurements. The calculations were checked and rechecked by astronomers around the world. The conclusion that this object had arrived from interstellar space was accepted only after exhausting all other possible explanations. Yet, even with this careful verification, mysteries remained. The unusual acceleration that Oumuamua exhibited as it departed the inner solar system challenged our understanding of how such objects should behave. Its extreme elongation or thinness differed from anything previously observed in our solar system. These anomalies didn't invalidate the discovery, but rather opened new questions about the diversity of objects that might exist in the galaxy beyond our sun's influence. This is perhaps the most beautiful aspect of cosmic listening, the way it reveals not just what we expected to find, but phenomena we never thought to look for. Each new discovery expands our sense of what's possible in the universe, challenging our assumptions and inspiring new questions that drive future observations. As night deepens around observatories across the world, astronomers continue their patient vigil. They scan the skies with instruments that grow more sensitive each year, accumulating data that may not reveal its significance for months or years to come. They listen to the universe with electronic ears tuned to frequencies of light invisible to human eyes, waiting for the next whisper of information from the cosmic dark. Somewhere out there, perhaps, another interstellar visitor is approaching our solar system, still too distant and faint to detect, but carrying its own cargo of mysteries from some distant star. When that moment of recognition comes, when human intuition recognizes the signature of the unprecedented in a sea of routine data, it will represent another small triumph in humanity's long effort to understand our place in the cosmic community. Until then, the listening continues, patient and persistent as starlight itself. There is something profound about the word second, the way it transforms the unprecedented into the beginning of a pattern. When Oumuamua first swept through our solar system, it stood alone in the category of confirmed interstellar visitors, unique and unrepeatable. But the universe, as it often does, had other plans. On August 30, 2019, nearly 2 years after Oumuamua's discovery, amateur astronomer Comet Borisov was conducting his routine sky survey from his small observatory in Crimea when he noticed something unusual moving against the background stars. The detection came not through the sophisticated networks of professional observatories, but through the patient work of a single individual with a modest telescope and an extraordinary dedication to watching the sky. Borisov had built his own instruments, ground his own mirrors, and spent countless nights systematically photographing the same regions of sky, looking for anything that moved in unexpected ways. His discovery reminds us that the universe sometimes reveals its secrets, not to the most powerful instruments, but to the most persistent observers. Feel the cool night air that might surround such an observer, the weight of solitude that comes with spending long hours beneath the stars. There is a particular kind of attention that develops in those who watch the sky with such dedication, a sensitivity to subtle changes, an intuitive feel for the rhythms of celestial motion. that can only be acquired through years of patient observation. The object that Borisov discovered would eventually be designated ʻOumuamua Borisov, the 2I indicating that it was the second confirmed interstellar object ever observed. But unlike Oumuamua, which revealed its interstellar nature only after careful analysis of its trajectory, ʻOumuamua Borisov announced its foreign origins almost immediately. As follow-up observations accumulated over the following weeks, it became clear that this new visitor was following a hyperbolic orbit even more obviously interstellar than Oumuamua's path had been. The implications of this second discovery rippled through the astronomical community, like waves spreading across still water. Where Oumuamua had been a singular anomaly, fascinating but potentially unique, ʻOumuamua Borisov suggested that interstellar objects might be more common than anyone had dared hope. 2 confirmed visitors in less than 2 years implied that such objects could be detected regularly, given sufficient observational resources and favorable circumstances. But ʻOumuamua Borisov brought more than just confirmation that interstellar objects exist. It offered something that Oumuamua had not: the unmistakable signature of a comet. As it approached the inner solar system and began to warm in the increasing intensity of our sun's radiation, ʻOumuamua Borisov developed the characteristic fuzzy appearance that distinguishes comets from asteroids. Gases sublimated from its icy surface, creating a tenuous atmosphere called a coma, and eventually forming the graceful tail that has inspired human wonder for millennia. This cometary activity provided astronomers with opportunities that Oumuamua's brief, enigmatic passage had denied them. When comets warm and begin to outgas, they release not just water vapor and carbon dioxide, but trace amounts of other compounds that can be analyzed through spectroscopy. These molecular fingerprints offer direct evidence of the chemical processes that shaped the comet's formation, clues to the environment of its distant birthplace. Picture this celestial visitor awakening as it journeys toward our sun. For millions or perhaps billions of years, ʻOumuamua Borisov had been frozen in the cold darkness between stars, its surface unchanged by weather or geological processes, its interior preserving chemical signatures from the early days of its parent star system. Now warmed by our sun's increasing radiance, it began to stir, releasing gases that had been locked in ice since before our solar system formed. The spectroscopic analysis of ʻOumuamua Borisov's coma revealed familiar molecules: water, carbon monoxide and cyanogen among them. These are the same compounds found in comets born in our own solar system, suggesting that the processes of planetary formation may follow similar patterns around other stars. The chemical composition was not exotic or alien, but comfortingly familiar, as if ʻOumuamua Borisov were a distant cousin returning home after a long journey. Yet this familiarity carried its own profound implications. If comets from other star systems contain the same basic ingredients as our own, it suggests that the chemistry of life, the carbon-based molecules that form the foundation of biological processes, might be distributed throughout the galaxy in ways we are only beginning to understand. Every interstellar comet that passes through our solar system carries with it a sample of conditions around other stars, a library of chemical information from worlds we will never visit directly. The study of ʻOumuamua Borisov also revealed subtle differences that spoke to its foreign origins. The ratio of different isotopes in its expelled gases suggested formation in conditions slightly different from those that prevailed in our own solar nebula 4.5 billion years ago. These isotopic signatures are like fingerprints, unique to specific environments and processes, and they confirmed what the orbital mechanics had already suggested: this visitor truly had come from somewhere else. As autumn progressed into winter, ʻOumuamua Borisov continued its stately approach toward the inner solar system. Unlike Oumuamua, which had been discovered only after making its closest approach to the sun, ʻOumuamua Borisov was found while still relatively distant, providing astronomers with months to plan detailed observations of its behavior as it warmed and became more active. Rest in the comfortable rhythm of seasonal change, the way winter gradually yields to spring, as ʻOumuamua Borisov slowly approached the warmth of our sun, after eons of cold wandering between the stars. The collaborative response to ʻOumuamua Borisov's discovery demonstrated how much the astronomical community had learned from the brief encounter with Oumuamua. Within days of Borisov's initial detection, observatories around the world were turning their attention to this new visitor. The Hubble Space Telescope began a systematic monitoring campaign. Ground-based telescopes, equipped with spectrographs, started analyzing the composition of gases flowing from the comet's nucleus. Radio telescopes searched for emissions from specific molecules that might reveal details about the comet's internal structure and composition. This coordinated effort produced a wealth of data that far exceeded what had been possible for Oumuamua High-resolution images revealed the detailed structure of ʻOumuamua Borisov's coma and tail, showing how the expelled gases formed complex patterns as they interacted with the solar wind. Spectroscopic observations tracked changes in the comet's activity level as it approached perihelion, its closest point to the Sun. Photometric measurements revealed the nucleus's rotation period and provided estimates of its size and albedo. The nucleus itself, the solid core from which all cometary activity originates, appeared to be roughly spherical and perhaps a kilometer in diameter. This was refreshingly normal compared to Oumuamua's bizarre elongation, suggesting that ʻOumuamua Borisov represented a more typical example of interstellar debris. Its behavior as it warmed followed patterns familiar from the study of solar system comets, with activity increasing predictably as it approached perihelion and then declining as it moved back toward the cold outer regions. Yet even in its familiarity, ʻOumuamua Borisov carried mysteries. The detailed analysis of its gas production rates suggested that its nucleus was unusually rich in carbon monoxide, more so than typical comets from our outer solar system. This enhanced CO content implied formation in an environment even colder than the Kuiper belt, perhaps in the outer regions of its parent star system, where temperatures barely exceeded absolute zero. The trajectory analysis that confirmed ʻOumuamua Borisov's interstellar origins also provided clues about its possible birthplace. Tracing its path backward through space and time, astronomers calculated that roughly 1 million years ago, this comet had passed within about 7 light-years of the red dwarf star Ross. While not close enough to definitively identify this star as the comet's origin, the encounter suggested that ʻOumuamua Borisov had been wandering the galaxy for at least that long, and possibly much longer. Consider the implications of such a journey. 1 million years ago, early humans were just beginning to use stone tools. Entire civilizations have risen and fallen, while ʻOumuamua Borisov drifted through interstellar space, following a trajectory shaped by the gravitational influences of countless stars. It has witnessed supernovas that lit up regions of the galaxy with brilliant radiation. It has passed through molecular clouds where new stars were being born, perhaps collecting trace amounts of interstellar dust on its ancient surface. The discovery of ʻOumuamua Borisov also highlighted the remarkable efficiency of modern sky survey systems, where Oumuamua had nearly escaped detection entirely. Discovered only weeks before, it would have faded beyond the reach of ground-based telescopes. ʻOumuamua Borisov was found early enough in its passage through the inner solar system to allow for comprehensive study. This early detection was partly due to luck, but also to the improving capabilities of automated survey systems that scanned larger areas of sky with greater sensitivity than ever before. The contrast between the two interstellar visitors was striking in almost every way. Where Oumuamua was dark, elongated, and inert, ʻOumuamua Borisov was active, roughly spherical, and bright enough to study in considerable detail. Where Oumuamua exhibited puzzling acceleration that suggested exotic properties, ʻOumuamua Borisov behaved exactly as expected for a normal comet responding to solar heating. Where Oumuamua offered only brief glimpses of its nature before disappearing back into the cosmic dark, ʻOumuamua Borisov provided months of observation opportunities. These differences raised as many questions as they answered. Were Oumuamua and ʻOumuamua Borisov representative of different populations of interstellar objects? Did they originate from different types of star systems, or undergo different evolutionary processes during their long journeys through space? The small sample size, just 2 confirmed interstellar visitors, made it impossible to draw definitive conclusions, but the contrast between them suggested that the space between stars might contain a diverse menagerie of objects with widely varying properties. Feel the gentle weight of uncertainty settling around these questions like evening mist. Science advances not through immediate answers, but through the gradual accumulation of observations that slowly reveal patterns in apparent randomness. As ʻOumuamua Borisov reached perihelion in December 2019 and began its journey back toward interstellar space, it carried with it the distinction of being the most thoroughly studied interstellar object in history. The data collected during its passage would keep researchers busy for years, analyzing subtle details of its composition, activity patterns, and physical properties. Each measurement added another piece to the growing puzzle of what exists in the spaces between stars. But perhaps more importantly, ʻOumuamua Borisov's discovery and successful observation demonstrated that interstellar objects could be studied as a class of phenomena rather than as isolated curiosities. The techniques developed for analyzing its composition and behavior could be applied to future visitors, The observational strategies that proved successful could be refined and improved. The international collaboration that made comprehensive study possible could serve as a model for future discoveries. The comet's gradual fading as it moved away from the sun marked not an ending, but a beginning. Somewhere out there in the darkness, other interstellar travelers are following their own ancient trajectories toward our solar system. Some may be dark and enigmatic like Oumuamua, others may be active comets like Comet Borisov. Still others may represent entirely new categories of objects that we haven't yet learned to recognize or understand. The patient observers who scan the skies each night, professional astronomers with billion-dollar telescopes, and dedicated amateurs like Comet Borisov with instruments they built themselves, continue their vigilant watch. They know that the next discovery might come at any moment, heralded by nothing more dramatic than a faint point of light that moves slightly faster than it should, in a direction that suggests a journey beginning somewhere among the distant stars. In the quiet darkness that surrounds us all, these cosmic messengers continue their ancient wanderings, carrying stories from stellar nurseries and planetary systems that formed when our own world was young. Each one that passes through our neighborhood offers a glimpse into the vast community of worlds that surrounds us, a reminder that our solar system is just one small part of a galaxy filled with wonders we are only beginning to discover. Rest in the comfort of this cosmic companionship, knowing that we are not alone in our journey through space and time. When you walk along a shoreline at night, the waves that reach your feet might seem random and chaotic, each one unique in its timing and intensity. But if you sit quietly and watch for a while, patterns begin to emerge. The rhythm of the tide, the way swells group together, the subtle relationship between wind direction and wave height. What first appeared as randomness reveals itself as a complex dance governed by forces both visible and hidden. The discovery of two interstellar objects within the span of just 2 years invited a similar kind of pattern recognition. Oumuamua and Comet Borisov, different as they were in almost every observable characteristic, represented the first glimpses of what might be a vast population of objects drifting through the spaces between stars. Like the first two pieces of an enormous jigsaw puzzle, they hinted at a picture too large and complex to grasp from such limited evidence. The differences between our two confirmed visitors were so dramatic that they challenged any simple assumptions about what interstellar objects might typically be like. Oumuamua appeared dark, elongated, and asteroidal, showing no signs of the cometary activity that astronomers had expected from an object originating in the ice-rich outer regions of another star system. Comet Borisov, by contrast, behaved exactly like the comets of our own solar system, developing a fuzzy coma and graceful tail as it warmed in our sun's increasing radiance. This diversity suggested that the space between stars might contain representatives of every type of small body that exists within planetary systems. Rocky asteroids blasted from inner regions, icy comets expelled from outer zones, and perhaps hybrid objects formed through processes we don't yet understand. Each star system in the galaxy, through the complex gravitational dynamics that accompany planetary formation, likely ejects countless small bodies into interstellar space. Over billions of years, this process would populate the galaxy with a vast diaspora of wandering objects, each carrying chemical and physical signatures from its birthplace. Rest for a moment in the vastness of this concept. Close your eyes and imagine the Milky Way galaxy as a slowly stirring ocean, filled with countless small travelers following currents too complex for any single mind to map completely. The theoretical models that astronomers use to estimate the population of interstellar objects suggest numbers that strain comprehension. Based on the detection of just 2 confirmed visitors, calculations indicate that at any given moment, several interstellar objects larger than a few tens of meters might be passing through the inner regions of our solar system. Smaller objects, fragments the size of houses or automobiles, could be far more numerous, perhaps numbering in the thousands within the orbit of Neptune at any given time. Most of these theoretical travelers would remain forever invisible to our current technology, too small and dark to reflect enough sunlight for detection. They would pass through our cosmic neighborhood in silence, their presence marked only by the gravitational influences they exert on space-time itself, effects far too subtle for us to measure with existing instruments. We live, it seems, in a galaxy more crowded with wandering matter than we ever suspected, most of it moving through space unobserved and unrecognized. The orbital characteristics of Oumuamua and Comet Borisov provided clues about the processes that might send objects into interstellar space. Both visitors approached our solar system with relatively low excess velocities, speeds barely above the minimum required to escape our sun's gravitational influence. This suggested that they had not been violently ejected from their parent systems, but rather gently shepherded into interstellar space through the kind of gradual gravitational interactions that occur during the chaotic early phases of planetary system formation. Picture the birth of a star system, a collapsing cloud of gas and dust that gradually flattens into a rotating disk, with a young star igniting at the center, and planets slowly condensing from the remaining material. This process is never perfectly orderly. Gravitational interactions between forming planets can scatter smaller objects into highly elliptical orbits, some of which eventually carry them beyond the reach of their parent star's gravity. Over millions of years, each star system likely ejects a significant fraction of its original small body population, sending these objects on wandering journeys that may last billions of years. The chemical analysis of Oumuamua Borisov's outgassing provided our first direct glimpse into the composition of material formed around another star. The water vapor, carbon monoxide, and other molecules detected in its coma were familiar from our own solar system's comets, but with subtle differences in isotopic ratios that confirmed its foreign origin. These measurements suggested that the basic chemistry of planetary formation might be remarkably consistent throughout the galaxy, governed by the same physical laws and working with similar raw materials wherever stars are born. Yet, the isotopic differences were significant enough to serve as fingerprints, unique markers that might eventually allow astronomers to trace interstellar objects back to their parent star systems, or at least to identify different populations based on their formation environments. Future spectroscopic studies of other interstellar visitors might reveal whether objects from metal-rich star systems differ systematically from those born around metal-poor stars, or whether comets from the outer regions of planetary systems carry different chemical signatures than those formed closer to their parent stars. Feel the gentle rhythm of your breathing as you contemplate these cosmic fingerprints, these molecular signatures that connect distant worlds to our own scientific instruments through the universal language of chemistry and physics. The study of interstellar objects also opens unexpected windows into the history of our own solar system. The same processes that scattered Oumuamua and Oumuamua Borisov into interstellar space must have operated in our cosmic neighborhood billions of years ago, ejecting countless objects from our forming solar system into the galactic medium. Some of these ancient emigrants might still be wandering the galaxy, carrying with them samples of the primordial material from which Earth and its sibling planets formed. The possibility of encountering such objects, interstellar artifacts of our own solar system's youth, adds a poetic dimension to the search for cosmic visitors. We might someday discover and analyze material that originated in our own stellar nursery but has spent billions of years exploring the galaxy before returning home. Such an object would be simultaneously foreign and familiar, an ambassador from our own deep past that could provide insights into conditions during the solar system's formation that no other type of observation could reveal. The detection rates for interstellar objects depend critically on the capabilities of our sky survey systems. The discovery of both Oumuamua and Oumuamua Borisov occurred during a period of rapid improvement in automated sky surveys, with telescopes capable of monitoring larger areas of sky with greater sensitivity than ever before. The upcoming Vera-Rubin Observatory, with its unprecedented ability to survey the entire visible sky every few days, promises to revolutionize the discovery and study of transient objects, including interstellar visitors. Current projections suggest that the Rubin Observatory might detect one interstellar object per year, transforming what is now a rare and precious discovery into a routine occurrence that allows for statistical analysis of interstellar population. Such regular discoveries would enable astronomers to study the diversity of interstellar objects, search for correlations between their properties and their probable origins, and perhaps even identify specific star systems or stellar associations as the sources of particular visitors. The prospect of routine interstellar object detection raises intriguing questions about what we might learn from a larger sample. Would most such objects resemble familiar asteroids and comets from our own solar system, or would we discover entirely new categories of small bodies that don't exist within our sun's influence? Would objects from different regions of the galaxy show systematic differences in composition or structure? Would we find evidence for exotic formation processes that operate only under conditions not present in our cosmic neighborhood? Rest in the anticipation of these future discoveries, like settling into a comfortable chair with a good book, knowing that fascinating stories await in the pages yet to be turned. The study of interstellar objects also provides unique opportunities to investigate the conditions that prevail in interstellar space itself. Objects like Oumuamua and Borisov have spent millions or billions of years exposed to the interstellar environment, a realm of extreme cold, intense radiation and tenuous gases that we can study in other ways but never directly sample. The surfaces of these objects preserve records of their long journeys, chemical and physical modifications that result from exposure to cosmic rays, interstellar dust impacts and other environmental factors. The reddish coloration observed on both Oumuamua and Borisov, for instance, likely results from the gradual processing of organic compounds by cosmic ray bombardment over geological timescales. This space weathering process operates much more slowly than the geological and atmospheric forces that modify surfaces within planetary systems, creating a kind of archaeological record of conditions during the object's long interstellar wanderings. Future studies of interstellar objects might reveal systematic relationships between surface properties and estimated travel times, providing insights into the rates of various space weathering processes. Objects with longer estimated interstellar residence times might show different degrees of surface modification than more recent escapees from their parent systems. Such studies could illuminate the physics of interstellar space and the timescales over which various processes operate in that extreme environment. The gravitational dynamics that govern interstellar object trajectories also provide opportunities to probe the distribution of mass within our galaxy. As these visitors travel through interstellar space, their paths are influenced by the gravitational fields of every massive object they encounter. Not just stars, but also a mysterious dark matter that appears to dominate galactic structure. Precise measurements of interstellar object trajectories, combined with detailed knowledge of their orbital histories, might eventually provide new ways to map the distribution of both visible and dark matter throughout the galaxy. Such investigations would require large samples of well-observed interstellar objects, along with computational models capable of tracking their complex gravitational interactions over millions of years. The chaotic nature of multi-body gravitational systems means that small uncertainties in initial conditions can grow into large uncertainties in predicted outcomes, but statistical analysis of many objects might reveal patterns that individual trajectories obscure. Consider the elegant connections that link these wandering visitors to some of the deepest questions in astronomy: the formation and evolution of planetary systems, the chemical history of the galaxy, the nature of dark matter, and the processes that operate in the vast spaces between stars. Each new interstellar object detection adds another data point to multiple ongoing investigations, contributing to our understanding of phenomena that span scales from the molecular to the galactic. The international collaboration required to study interstellar objects effectively also represents something beautiful about modern astronomy. The way that discoveries made by observers in one part of the world can be immediately shared with colleagues everywhere, leading to coordinated campaigns that maximize the scientific return from brief observational windows. The follow-up observations of both Oumuamua and Borisov involved telescopes on multiple continents, space-based observatories and researchers from dozens of institutions working together toward common goals. This collaborative spirit reflects astronomy's fundamental character as a human enterprise that transcends national boundaries and individual ambitions. The universe belongs to everyone, and its secrets are best revealed through shared effort and open exchange of information. The study of interstellar objects exemplifies this principle, requiring rapid coordination between observers, theorists, and instrument specialists to make the most of fleeting opportunities. As we continue to discover and study these cosmic wanderers, we are gradually constructing a new kind of map, not of places we can visit, but of the invisible currents and populations that connect star system to star system across the galaxy. Each interstellar object detection reveals another thread in the vast web of gravitational and chemical relationships that binds our cosmic neighborhood together. In the gentle darkness that surrounds all our earthbound observations, countless such objects continue their ancient journeys, carrying stories we have only begun to learn how to read. Some approach from the direction of familiar constellations, while others arrive from regions of sky that hold no bright stars visible to the naked eye. All of them represent connections to distant worlds, samples of matter formed under alien suns, and opportunities to extend our understanding beyond the comfortable boundaries of our own solar system. The patterns we are beginning to glimpse in this sparse data promise richer revelations as our sample grows. Like archaeologists reconstructing ancient civilizations from scattered artifacts, Astronomers are using these rare visitors to piece together a picture of galactic dynamics and planetary system evolution that encompasses scales of time and distance beyond direct human experience. Rest in the profound patience this work requires, the willingness to build understanding piece by piece, observation by observation, across decades and centuries of accumulated human effort. Memory, in the human sense, is a fragile and subjective thing. We remember selectively, transforming experiences through the lens of emotion and time, losing details while amplifying meanings. But there are other kinds of memory in the universe, more patient, more literal, more enduring. The rocks beneath our feet remember the pressure of ancient seas, ice cores preserve samples of prehistoric atmospheres, and wandering through the darkness between stars, objects like Oumuamua and Comet Borisov carry their own forms of memory, written not in neurons or consciousness, but in the physical and chemical signatures that record their long journeys through space and time. Consider what Oumuamua has witnessed during its journey to our solar system. If we trace its trajectory backward through the galaxy, following the gravitational dance of stars and the slow rotation of spiral arms, we find that our visitor has been traveling through interstellar space for millions, perhaps tens of millions of years. During that vast span of time, entire mountain ranges have risen and eroded away on Earth. Species have evolved and gone extinct. Ice ages have come and gone, reshaping continents and coastlines. But Oumuamua, in its cold isolation, has preserved a more ancient perspective. Its surface, darkened and reddened by eons of cosmic ray bombardment, remembers conditions that prevailed in interstellar space when our own species was nothing more than a distant possibility. Every crater and ridge on its tumbling form tells a story of impacts with interstellar dust grains, each collision a tiny mark left by the sparse matter that fills the spaces between stars. Feel the deep stillness that surrounds such journeys, not the familiar quiet of earthly nights, but the profound silence of vacuum, broken only by the occasional impact of cosmic dust or the subtle pressure of starlight itself. The isotopic ratios locked within these object structures carry even deeper memories. When Comet Borisov released its cargo of water vapor and carbon monoxide as it warmed in our sun's increasing radiance, those molecules carried chemical signatures from the stellar nebula where the comet first formed. The specific proportions of different isotopes, atoms of the same element with slightly different masses, depend on the nuclear processes that operated in the comet's parent star and the conditions that prevailed in the protoplanetary disk, where solid matter first condensed. These isotopic fingerprints are like genetic markers, connecting each interstellar visitor to the specific environment of its birth. The slight differences between the isotopic ratios in Comet Borisov's outgassing and those found in our solar system's comets speak to subtly different formation conditions. Perhaps a parent star with a different metallicity, or a protoplanetary disk that evolved under different temperature and pressure regimes. In this way, every interstellar object serves as an emissary, carrying direct samples of matter from distant stellar nurseries. We cannot yet travel to other star systems to study their planetary formation processes directly, but these cosmic messengers bring fragments of other worlds to us, allowing us to analyze alien matter in our own laboratories and extend our understanding of how planetary systems form throughout the galaxy. The journey itself becomes part of the story these objects tell. During their long wandering between stars, interstellar objects experience conditions unlike anything found within planetary systems. The temperature of space far from any star approaches absolute zero, barely 3 degrees above the point where all molecular motion ceases. In this extreme cold, even the most volatile substances freeze into solid form, preserving chemical compounds that would be unstable under warmer conditions. The radiation environment of interstellar space is equally extreme, but in a different way. Cosmic rays, high-energy particles, accelerated by supernova explosions and other violent events, streak through the galactic medium at nearly the speed of light, occasionally striking the surfaces of wandering objects with enough energy to break chemical bonds and create new molecular species. This slow cosmic chemistry operates over millions of years, gradually modifying surface compositions in ways that record both the intensity of galactic radiation and the duration of interstellar exposure. Picture Oumuamua during one of these cosmic ray impacts. A single high-energy proton, accelerated by some ancient stellar explosion perhaps thousands of years ago, finally completing its journey across the galaxy by striking our visitor's dark surface. The impact creates a tiny spray of secondary particles, breaks apart a few organic molecules, and leaves behind a microscopic crater that will persist for millions of years, one small mark among countless others that together document the object's long exposure to the interstellar environment. The magnetic fields that thread through interstellar space also leave their subtle signatures on these traveling archives, though far weaker than the magnetic fields we experience on Earth. Interstellar magnetic fields can influence the trajectories of charged particles and may affect the chemistry of surface materials over very long timescales. Objects that have wandered through regions of particularly strong magnetic activity might carry different chemical signatures than those that have traveled through magnetically quiet zones. Rest in the vastness of these timescales, the way millions of years compress into a single moment of contemplation, like watching clouds form and dissolve in time-lapse photography. The gravitational memories encoded in these objects' trajectories tell stories of stellar encounters that occurred so long ago they predate most features of our current landscape. When astronomers calculated that Oumuamua Borisov had passed within 7 light-years of the red dwarf star Ross 57-3 about 1 million years ago, they were reading a record written in orbital mechanics, the way gravity shapes trajectories across cosmic distances and geological timespans. Such encounters leave permanent marks on interstellar trajectories, subtle changes in velocity and direction that accumulate over millions of years to produce the complex orbital paths we observe today. By studying these gravitational signatures, astronomers can begin to reconstruct the galactic environment through which these objects have passed, identifying stellar encounters and mapping the distribution of mass throughout regions of space that we may never visit directly. The thermal memories preserved in these objects' interiors may be the most remarkable of all. The cores of large interstellar objects, insulated by layers of surrounding material, can preserve temperatures and chemical conditions from the early phases of their formation. Unlike the surfaces, which are constantly modified by radiation and impact processes, the deep interiors of these cosmic time capsules may contain pristine samples of matter from their birth environments. Future missions to intercept and sample interstellar objects might find that their cores preserve not just the chemical signatures of alien star formation, but actual fragments of the primordial materials from which other planetary systems formed. Such samples would be like archaeological artifacts from stellar nurseries, allowing us to study the raw materials of planet formation under conditions that may have been very different from those that prevailed in our own solar nebula. The rotational states of interstellar objects also carry information about their histories. The way Oumuamua tumbled as it passed through our solar system, rotating about its shortest axis with a period of 7.3 hours, speaks to the complex gravitational interactions that shaped its motion during ejection from its parent system or subsequent encounters with other massive objects. The specific combination of rotation rate and orientation represents a kind of mechanical memory, preserving information about ancient collisions or tidal encounters in the form of angular momentum. Even the absence of certain features can carry meaning. The fact that Oumuamua showed no signs of cometary activity as it warmed in our sun's radiance suggests either that it formed in the rocky inner regions of its parent system, or that its surface materials had been processed in some way that removed or altered their volatile components. This absence tells a story as surely as presence would, a negative image that helps define the conditions under which the object formed or the processes it experienced during its interstellar journey. Consider the profound loneliness of such journeys. For millions of years, these objects have traveled through regions of space so empty that matter is scarcer than in the best vacuum chambers we can create on Earth. The nearest star appears as nothing more than a bright point of light, no different from the countless other stars scattered across the sky. There are no seasons, no weather, no geological processes, only the slow, inexorable effects of cosmic radiation and the occasional impact of interstellar dust. Yet, in this apparent emptiness, subtle processes continue to operate. Magnetic fields shift and flow like invisible rivers. Clouds of gas and dust drift between star systems, sometimes dense enough to produce measurable effects on passing objects. Gravitational waves from distant cataclysms ripple through space-time itself, carrying energy across the galaxy at the speed of light. The interstellar medium is not truly empty, but filled with phenomena too subtle for our direct senses to detect. The objects that wander through this environment serve as passive sensors, recording conditions through their slowly accumulating modifications. Like deep-sea sediments that preserve climate records in their layered deposits, The surfaces of interstellar objects build up archaeological records of galactic conditions over millions of years. Each chemical change, each impact crater, each structural modification adds another entry to a logbook written in the language of physics and chemistry. The memories these objects carry extend beyond their own individual histories to encompass the broader story of galactic evolution. The heavy elements locked in their compositions were forged in the nuclear furnaces of ancient stars, dispersed through space by supernova explosions, and incorporated into new generations of stellar and planetary systems. Every carbon atom in an interstellar comet's organic compounds, every iron atom in an interstellar asteroid's metallic matrix, carries the signature of nucleosynthesis processes that operated billions of years ago in stars that have long since ended their lives. In this sense, interstellar objects are libraries of cosmic history, their very existence testament to the long, complex processes that have shaped our galaxy over billions of years. They connect the present moment to epochs so remote that our imaginations struggle to encompass them, yet their presence in our solar system makes those ancient times as real and immediate as the ground beneath our feet. Feel the weight of deep time settling around you like a comfortable blanket. The way these cosmic memories connect us to stories that began long before our world existed, and will continue long after our sun has faded to a white dwarf. The study of these traveling archives requires a kind of detective work that operates across multiple disciplines. Spectroscopists analyze the light reflected from their surfaces to identify chemical compounds. Dynamicists trace their trajectories backward through time to map their possible origins. Cosmochemists compare isotopic ratios to understand formation conditions. Planetary scientists model the processes that might have shaped their structures and compositions. Each analysis reveals another layer of the story, another aspect of the complex histories these objects carry. Like archaeologists reconstructing ancient civilizations from fragmentary evidence, astronomers piece together narratives that span millions of years and light years of space, using every available clue to understand not just what these objects are, but where they came from and what they experienced during their long journeys to our solar system. The implications extend beyond astronomy into philosophy, and perhaps even into our understanding of consciousness itself. If memory can be encoded in chemical signatures and physical structures, if the history of cosmic events can be preserved in the isotopic ratios of wandering rocks, then perhaps memory is a more fundamental property of the universe than we commonly suppose. Perhaps everything carries traces of its history, written in languages we are only beginning to learn how to read. The interstellar objects that visit our solar system are messengers from this deeper kind of memory. Cosmic veterans carrying stories from stellar environments we may never observe directly. Their dark surfaces have witnessed the births and deaths of stars. Their ancient trajectories have been shaped by gravitational encounters with objects whose very existence we can only infer from the subtle changes in orbital mechanics. Their chemical compositions preserve samples of matter from protoplanetary disks that formed when our own solar system was nothing more than a diffuse cloud of gas and dust. In welcoming these visitors, we open ourselves to perspectives that transcend the boundaries of our immediate cosmic neighborhood. We become temporary custodians of archives that connect us to the broader community of worlds that surrounds us, repositories of experience that span scales of time and space that challenge our earthbound intuitions about memory, permanence, and connection. As these objects continue their journeys back into the darkness between stars, they carry with them new memories, brief records of their passage through our solar system, subtle modifications produced by their encounter with our sun's radiation and gravitational field. In some small way, they now remember us too, carrying traces of their visit to our cosmic neighborhood into the vast spaces where other civilizations might someday detect and study them. Rest in this gentle reciprocity, the way memory flows in all directions through the universe, connecting past to future, star to star, and world to world through the patient journeys of matter itself. There comes a moment in every farewell when you realize that the departure has already begun, that the distance is growing even as you stand watching, even as you imagine yourself still connected to what is leaving. For Oumuamua, that moment came, not with drama or fanfare, but with the quiet mathematics of fading light. By January 2018, our first confirmed interstellar visitor had become too dim for even our most powerful telescopes to track. It continued its journey toward the constellation Pegasus, carrying its secrets back into the vast darkness from which it had emerged. The silence that followed Oumuamua's departure was not empty. but full of questions that would ripple through the astronomical community for years to come. What had we really seen during those brief months, when our cosmic visitor reflected enough sunlight for human instruments to decode? A fragment of alien architecture, as some had tentatively suggested? A natural formation unlike anything in our own solar system, or simply the first of what would prove to be many such wanderers, each bringing its own cargo of mysteries from the spaces between stars? In this uncertainty lay something beautiful. The reminder that the universe still holds surprises for us, still offers phenomena that challenge our assumptions and expand our sense of what is possible. Oumuamua had been humanity's first confirmed glimpse of matter from another star system, but it refused to fit neatly into any of the categories we had prepared for such visitors. Its elongated shape, its unusual acceleration, its lack of cometary activity, all of these characteristics marked it as something genuinely unprecedented in our experience. Feel the gentle rhythm of your breathing as you contemplate this cosmic modesty, the way the universe offers its revelations, not as grand pronouncements, but as subtle invitations to look more carefully, think more deeply, remain open to possibilities we haven't yet imagined. Oumuamua Borisov, our second interstellar visitor, provided a different kind of farewell when it too faded beyond detection in late 2020. Unlike Oumuamua's enigmatic departure, Borisov's exit felt almost familiar. The predictable dimming of a comet as it moved away from the sun's warmth, its activity declining in ways that matched our understanding of how such objects behave. Yet even this familiarity carried its own profundity, confirming that the processes of planetary formation might follow similar patterns throughout the galaxy, that the chemistry of life's building blocks might be more widely distributed than we had dared hope. The contrast between these two departures highlighted the range of possibilities that await us in future encounters with interstellar objects. Some may prove as puzzling as Oumuamua, challenging our theories and forcing us to expand our understanding of what can exist in the universe. Others may be as reassuring as Oumuamua Borisov, confirming our models and extending our knowledge of familiar processes into new environments. Both types of discovery have their place in the larger story of how we come to understand our cosmic neighborhood. As these visitors receded into the darkness, they left behind more than just scientific data and theoretical puzzles. They had fundamentally changed our relationship with the space around our solar system. Before Oumuamua, the realm beyond Pluto's orbit seemed empty and static, a frontier that we might someday explore with robotic probes, but that offered little immediate relevance to our understanding of the present moment. After Oumuamua, that same space became dynamic and populated, filled with the possibility of encounters that could arrive at any time. This shift in perspective touches something deeper than astronomy. It speaks to our fundamental relationship with impermanence, with the way that everything in the universe, from individual lives to entire galaxies, exists in a state of constant motion and change. The interstellar objects that visit our solar system are particularly poignant embodiments of this cosmic impermanence, appearing briefly in our telescopes before continuing journeys that began long before our species existed and will continue long after our sun has exhausted its nuclear fuel. Picture Oumuamua as it moves through space today. Several years after its departure from our solar system, by now it has passed beyond the orbit of Saturn, its surface temperature dropping toward the background temperature of interstellar space. The faint warmth it absorbed during its passage near our sun has radiated away into the void. Once again, it experiences the profound cold and silence that characterized most of its multi-million-year journey to reach us. In a few more years, Oumuamua will cross the orbit of Neptune and enter the outer regions, where our sun's influence begins to fade into the general galactic background. The gravitational field that briefly captured and redirected its trajectory will release its hold, and our visitor will return to the straight-line motion through interstellar space that characterized its approach to our solar system. The hyperbolic arc that brought it through our cosmic neighborhood will be complete, a graceful curve that connected two epochs of linear drift through the vast spaces between stars. Rest in the profound patience this journey requires, the willingness to continue moving through emptiness for millions or billions of years, carrying ancient memories toward destinations that may never arrive. The mathematical models that describe Oumuamua's future trajectory can follow its path for thousands, even millions of years into the future. In about 11,000 years, it will pass within 2 light-years of the star Ross 208 in the constellation Andromeda. In 20,000 years, it will have a more distant encounter with the bright star Vega, whose light guided its initial approach to our solar system. These future meetings will be as brief and inconsequential as its passage through our solar system. Gravitational encounters that will slightly modify its trajectory without significantly altering its overall journey through the galaxy. But beyond such calculable encounters lies a future shrouded in the fundamental unpredictability of multi-body gravitational systems. Small uncertainties in Oumuamua's current position and velocity will grow over time, making precise long-term predictions impossible. After a few million years, we can say little more than that. Our former visitor will continue wandering somewhere within the general region of the galaxy where we encountered it, its exact position and trajectory lost in the chaotic complexity of interactions with countless stellar gravitational fields. This mathematical horizon, beyond which prediction becomes meaningless, serves as a metaphor for the limits of all human knowledge. We can trace stories backward into the deep past and project them forward into the distant future, but always within boundaries set by the finite precision of our measurements and the inherently probabilistic nature of complex systems. The universe preserves its essential mystery even as it reveals its secrets, offering us glimpses of cosmic processes while maintaining an inexhaustible capacity for surprise. The search for additional interstellar objects continues in observatories around the world, driven by the knowledge that Oumuamua and Comet Borisov represent not isolated anomalies, but the first detected members of a vast population. The Vera-Rubin Observatory, scheduled to begin full operations in the coming years, will survey the entire visible sky every few nights with unprecedented sensitivity. Its systematic monitoring of the southern sky promises to detect interstellar objects as a matter of routine rather than exceptional luck. Future discoveries will undoubtedly include objects that challenge our understanding in new ways, visitors that carry chemical signatures from stellar environments, unlike any we have previously encountered, or physical properties that suggest formation processes we haven't yet learned to recognize. Each new detection will add another piece to our slowly developing picture of the galactic community to which our solar system belongs, revealing new aspects of the diversity and complexity that characterize the spaces between stars. But perhaps more important than any specific discovery will be the gradual shift in human perspective that comes from regular encounters with matter from other star systems. As interstellar objects become familiar rather than extraordinary, as their study becomes a recognized subdiscipline within astronomy, we will be taking another step in the long process of expanding our cosmic perspective beyond the boundaries of our immediate neighborhood. This expansion of perspective has characterized human intellectual development for centuries. We have learned to see our Earth as one planet among many, our Sun as one star among billions, our galaxy as one of countless others scattered throughout the observable universe. The recognition that our solar system exists within a larger community of worlds, connected by the constant exchange of wandering matter, represents another milestone in this ongoing journey toward cosmic maturity. Feel the comfort of this larger perspective, the way it places our individual lives and concerns within a context vast enough to contain all possibilities, gentle enough to hold all sorrows, and beautiful enough to inspire wonder that transcends the boundaries of any single lifetime. The long goodbye that began with Oumuamua's departure continues today, as that object moves through the outer regions of our solar system, and it will continue tomorrow as it enters the interstellar medium and for millions of years beyond. As it wanders through regions of the galaxy we will never explore directly, this is not the kind of farewell that reaches resolution or closure, but rather a gradual fading that asymptotically approaches but never quite reaches a final ending. In this extended departure, there is something that mirrors the way all meaningful connections persist, even after physical separation. The influence of Oumuamua on human understanding of the cosmos will continue long after the object itself has vanished beyond all possibility of detection. The questions it raised will drive new research for decades to come. The techniques developed to study it will be refined and applied to future discoveries. The sense of wonder it inspired will motivate new generations of astronomers to keep watching the skies with patient attention. The physical object may be fading into undetectable insignificance, but its impact on human consciousness has achieved a kind of permanence that transcends the merely material. This transformation from wandering rock to cultural artifact, from cosmic debris to scientific inspiration, represents one of the most remarkable aspects of the encounter between human curiosity and the vast universe that surrounds us. Comet Borisov underwent a similar transformation during its passage through our solar system, evolving from astronomical object to scientific treasure to cultural touchstone. Its more familiar behavior made it less mysterious than Oumuamua, but no less significant as a confirmation that interstellar visitors could be studied as a class of phenomena, rather than as isolated curiosities. The data collected during its extended observation campaign continues to yield new insights about the composition and behavior of comets formed around other stars. The legacy of both visitors extends beyond their individual characteristics to encompass the methods developed for their study and the collaborative networks that made comprehensive observation possible. The rapid mobilization of international astronomical resources that followed each discovery established precedents for future encounters, creating institutional frameworks that can respond quickly when the next interstellar object appears in our telescopes. These organizational achievements may prove as important as the scientific discoveries themselves, representing humanity's growing capacity to act as a unified species when confronted with phenomena that transcend national boundaries and individual interests. The study of interstellar objects requires coordination across time zones and continents, sharing of resources and expertise that reflects our best aspirations for international cooperation. As you rest in the quiet of this moment, consider the invisible threads that connect your immediate experience to these cosmic journeys. The carbon atoms in your body were forged in stellar furnaces, similar to those that created the heavy elements in interstellar objects. The gravitational forces that hold you to Earth are fundamentally the same as those that shape the trajectories of wandering asteroids and comets. The electromagnetic radiation that carries information from these distant visitors to our telescopes operates according to the same physical laws that govern the light by which you see and the neural processes by which you think. These connections are not merely metaphorical, but literally true, expressions of the deep unity that underlies the apparent diversity of cosmic phenomena. We are not separate observers studying foreign objects, but participants in the same vast story of matter and energy that connects every atom in our bodies to every star in the sky, and every object that wanders through the spaces between them. The long goodbye that began with our first glimpses of interstellar visitors will continue throughout our lifetimes and beyond, as these objects carry their cargo of memories and mysteries back into the galactic medium from which they emerged. But this departure is also an arrival, the beginning of humanity's recognition that we live, not in isolation but as part of a dynamic galactic community where matter flows constantly between star systems, carrying information and possibility across distances that challenge our imaginations. In learning to see and study these cosmic messengers, we have taken another small step toward understanding our place in the larger universe. We have confirmed that the space around us is more dynamic and interconnected than we previously realized. We have demonstrated our growing capacity to recognize and analyze phenomena that our ancestors could never have imagined, and we have opened new windows into the diversity and wonder that characterize the cosmos beyond our immediate perception. The night sky that surrounds us as we rest contains countless other stories waiting to be discovered, countless other connections between distant worlds and our own small planet. Some of these stories will arrive as faint points of light moving against the background stars. Others will whisper to us through gravitational waves or exotic particles or forms of electromagnetic radiation we have yet to learn to detect. But all of them will share the essential characteristic that made Oumuamua and Comet Borisov so compelling. They will remind us that we are part of something larger than ourselves, something more ancient than our species, something more wonderful than our current understanding can fully encompass. In this reminder lies both humility and inspiration, the recognition of how much we have yet to learn, and the joy of knowing that the universe still holds countless surprises for those patient enough to watch and wise enough to wonder. Sleep well in the knowledge that the cosmos continues its ancient dance around us, that somewhere in the darkness above, other wanderers are following their own mysterious trajectories toward encounters we cannot yet predict or imagine. Their stories will unfold in their own time, revealing new chapters in the endless book of cosmic connection and discovery that links our small world to the vast community of worlds that surrounds us. The long goodbye continues, patient as starlight, gentle as gravity, and endless as the space between stars.